welcome to a brief discussion about the binomial distribution. Today, I'm not actually going to be talking and explaining to you the entire basis of the binomial distribution. What I'm going to do is explain to you how this relates back to something we talked about at the original the first day of class, which is our introduction to statistical inference. And we had given you a worksheet posted on D2L describing the basic introduction to an inferential process. Well, it turns out that this particular inferential process is based on, ta-da, a binomial distribution. And so what I'd like to do is talk a little bit about how this picture relates to something we can do in StatCrunch with the binomial distribution. So it's probably been a couple weeks for you. If you don't recall this, I'd ask that you take a little bit of time to review this worksheet, and what I will ask you to do is pause the video momentarily while you do so. Now that you've caught up with the context of what we're working in, I'm going to talk a little bit about this graph over here. So we had 100 unskilled tea tasters. What that meant was that each tea taster was guessing whether each cup was milk or tea poured first. And each person got to try 12 cups. So we counted up how many cups they got correct, as if working as though they were guessing. Well, now it turns out that such a situation is perfect for a binomial. Each of our tea tasters has an x equal to number of cups correct out of 12. Now I'm going to ask you to think about why x has a binomial distribution, and you can again pause the video here if you'd like to do that. The reason is, of course, that we're counting up the number of one of two outcomes, either the cup is correct or it's not, out of 12, a fixed number of outcomes, presumably independent. It doesn't matter what you think from one to the next or what you say from one to the next. And same probability of success. If they're guessing, the probability of success is half, 50-50. So x has a binomial distribution with 12 cups and probability of success 0.5 due to guessing. And so for every tea taster, we had an x, and we made a histogram or a dot plot up here of those different x values. Well, what I'd like to do is bring us over to StatCrunch and think about how the probability distribution for the binomial relates to this picture. Okay. Now when you open up StatCrunch, as I did from over here in my stat lab, it allows you to type in information. What I did was I typed in an x value for each value that my binomial random variable can take. Now since we're counting up the number of successes out of 12, that's the max possible value. And I could, in theory, have 0 successes. So any integer from 0 to 12 could be in my number of successes. Now what I'm going to do is calculate and visualize the probability of getting each of these numbers of cups correct. And if you like, you can even type that up here. X equals number of cups correct. Something like that. And it doesn't display the whole thing, so maybe we don't want to put that whole thing in there. Number correct. All right. So I'm going to go into Stat, Calculators, and Binomial. What this does for me is allows me to enter n equals 12, probability of success, and then I want to know the probability that x equals each particular value. Now, if you take a look at the shape should look awfully familiar. It's the same shape we saw over here. Now, granted, one's squished down a little bit more, but it's the same deal. And in fact, we can get a rough idea of the probabilities over here by taking them out of 100. So over here, my rough idea of, say, the number of people who got 8 cups correct. Let me switch back over here. The number of got 8 cups correct out of 12. Let's see, 2, 4, 6, 8, 10, 11. So my rough idea is about 11% of people, when guessing, would get 8 out of 12 cups correct. So let's take a look at that over here. Probability x equals 8, and I'm going to compute. Hey, look at that, pretty close. 12%, so about 12 out of 100. But again, we only had 100 over here, so that's not a long-term probability. This is the true long-term probability. So if we did this a whole bunch more times with a whole bunch more tea tasters, we would get close to 12% of them getting 8 cups correct. Well, another question that we'd had, what might we think if Lady X correctly identified 11 or 12 of the pores? In our picture up here, it didn't look like there were many people who got 11 or 12 correct. Well, let's take a look at the probability that X is greater than or equal to 11, because greater than or equal to 11 means 11 or 12. And look at that. Less than 0.5% of all people would get 11 or 12 cups correct if they were just guessing. So that's why it leads us to conclude that if Lady X got 11 or 12 of them correct, gosh, we're starting to think that she really knows what she's talking about, because it would be so unlikely, remember, a probability of less than 0.5% of happening if she was just guessing. We don't think she's just guessing. And that is our heart of inference. But notice that it also is an inference based on the binomial distribution. And you'll see even more of this when you get to chapters 9 and 10 and start dealing with confidence intervals and hypothesis testing. Okay. So that's a little bit of how you use the binomial calculator and a little bit about how that connects to inference. And we'll revisit this a little bit more when we get into our Chapter 8 and sampling distributions about a proportion. Thanks for your attention today. Bye.